Hello, welcome to our short tutorial series in this sequence of lectures about differential equations. On the last few lectures, we explained to you the importance of differential equations, and we also showed to you some of the main techniques to solve the differential equations, right? And we always emphasize that building the differential equation when you are dealing with a problem is as important as solve the differential equation, right? Because differential equation, they represent some physical problem or some situation where you want to see the relation between variation of some quantities with respect to some variables. And in the last lectures, we concentrate on the use of a power series to solve a differential equation. You know, we know that almost all the functions can be expressed in terms of a series. So we said, well, okay, the solution of differential equation is a function, so can be expressed in terms of a series, a power series. And we explained to you in few words how to deal with the problem and how to express this whole series, and sometimes even to close as an analytical expression for the function. Today we're going to use another technique. There are many different ways to solve equation. You know, we are far from exhaust the ways of solving the problem. And today we're going to speak about an important technique that's called Laplace transform for solving differential equation. Laplace transform, everybody hear about Laplace, very famous mathematician, and we all learn in calculus, Laplacian and things like this. But Laplace proposed a way to transform function in another function. This is very common in mathematics. We take a function, we do some modification, and instead of expressing the function in terms of the variable, we express in terms of another variable, which are related to the first in some sense. And in most of the time, we apply transformations when we can make the problem easier to solve. And Laplace transformation is one of those techniques. And we are able to transform some equation in something much easier to solve, right? By doing a transformation of variables. And normally this transformation is not only substituting variables, it's making a whole integral of the original function. So this is the Laplace transform. So we're going to see today how to use the Laplace transform technique for solving differential equation. So the transformation of Laplace makes the differential equation somehow easier to solve. So the idea, let me explain to you what is the idea, you know, behind using transformation to solve a differential equation. And normally we have a differential equation. So suppose we have a differential equation. So here we have a differential equation, and we all know, we all learn at this point that a differential equation is a relation between derivatives of a function that we need to determine and that express some quantity that we are interested to know the behavior as a function of time or as a function of x or whatever is the independent variable that we have chosen. So we have this equation, and normally you have an expression that relates all derivatives, sometimes stop in the first order, sometimes second, sometimes third, and so on. You can have differential equations that relate to very high orders of derivatives with others and so on. You know, differential equations can be of very, very complex or very, very complicated collection. It's a mathematical expression that may involve many differential orders of derivatives. And the idea using Laplace transformation is very simple. Let's define some ways to modify the equation by making a transformation of the functions. So we're going to transform a differential equation in an algebraic equation. So we take the equation that involves derivatives, and we're going to make a function that involves only functions square, or does not involve really derivatives. So we transform a problem that we know that's hard to deal with are the derivatives, or sum of derivatives, or subtractions, or multiplications sometimes, in an algebraic equation that has no derivatives. Very interesting. So imagine I have an example for you. I have a second order differential equation. So I have the second derivative of a function plus something times the first derivative of a function plus a function equal to another function. And I want to find the original function. This is an equation involving different orders of derivative. Suppose that I make a transformation that instead of appearing second order derivative will appear some function square or some function. So I transform whatever is derivative in different orders into an algebraic equation. And it's like transform a differential equation of second order in a second order algebraic equation to know, like x squared plus some number times x plus another thing equal to 0. So that algebraic equation can be solved, and then we try to recover the original function. So making a transformation of a differential equation is to transform the equation in this sense, because the Laplace transform, right? We could make a variable substitution. Of course, this is a trick that we use all the time to solve differential equations. But it's not what we're doing here. Here is like going to different space. It's like saying, well, a differential equation can be mapped in a different way when we consider another system of coordinates, we go to a different space, right? And it works because we simplify. It's much easier to solve an algebraic equation than to solve a differential equation. If we can make this transformation, we already simplify, because now what we do, we solve this algebraic equation. So we solve the equation because we know how to solve algebraic equation. You know, we know how to solve a polynomial equation, second order, first order, second order, third order, and so on. We learned that, how to solve. So we solve that. And then what we do, we're going to get a function that's not exactly the original function. Let me tell you that when we do the transformation, when we go from a sequence of derivatives like, functions that depend on x, for instance, when we do the transform, actually we go to another type of function which depended to another variable. So we change it, we go to another space, in fact. You understand? So we make this modification, and then we solve in this new function. But since we know how to transform equation or the function y in some equation, in some function f of s, we are able to now solve the equation in f and do the inverse transformation. Now we take the problem and we return to the original function. We learned that many equations are much simpler when we do some modifications, some transformations. And here is a specific type of transformation. It's called an integral transformation. And by doing this integral transformation, that is a famous transformation, Laplace transform of a function, is something very much used in many, many different situations. Here for the differential equation, this transformation helps us to transform a differential equation in an algebraic equation. It's like having many orders of derivative, and here we're going to have an equation that has different powers of the function. And by solving that and being able to apply the inverse transformation, we return and finally we have the solution. This is the principle that comes together with doing integral transformation in differential equations, right? And if you get used to, you solve the equation, very complex equation, you can solve in a very simple way. We're dealing with differential equation, but this method of Laplace transform can be used even for integral equations. Integral equations normally are even harder than differential equations. But, you know, thanks to very imaginative and intelligent people, we are able to apply methodology that can solve the problem. So basically, solving a problem by using Laplace transform is like solving an algebraic equation, which is easier than to solve the differential equation and comes back. So it is actually transforming the differential equation in something easier to solve, which is an algebraic equation. Solving the algebraic equation, we come back to the original function. So it's like making a transformation that makes everything easier in the solution. So that's the principle of the Laplace transform. But we have to understand the first what is Laplace transform, to be able to apply to the differential equation and to be able to solve some examples of differential equation. So let me start trying to explain to you what is a Laplace transformation. What transformation can we do in the equation that will make it easier? And as I keep saying in the lecture, we're going to do what we call Laplace transform. And to define a Laplace transform, let me tell you that most of the time, knowing the behavior of the function as it goes to asymptotic values, large values of the variable, limits of the variable, right? That helps a lot in solving equation. There are many methods in solving differential equations. One of them is see the terms that are important and go to a asymptotic regime. In physics, we use that all the time. We have an equation that describes a problem. We normally go and say, well, look, when I am in a very long time, probably this term is not important anymore. Then we solve, and then we return, and then we get we know part of the solution, and we're going to constructing the solution. This is another method for solving differential equations. But Laplace try to see the following. Laplace understanding that the exponential behavior is very important, because this is a very reference in functions. If the function has exponential behavior as the variable gets big, we know how these solutions explode when we go to high variables or goes to zero and things like this. So Laplace takes that into account. For me to explain Laplace transform to you, let's start with the function. So we're gonna say that we have a function, and this function, right? Probably this is what we're looking into a differential equation, is a specific function that we call y, or we call f, or we call whatever we want, right? And we have a function that is a defined function for all values of time, of the variable, independent variable. Here's the time, or t. It could be x. That's not the point. you know, whatever is the variable that we are dealing, that's not the problem, you know. You have to be very relaxed. Equations can be related to space, can be related with time, can be related to so many different variables. Can be related with temperature, can be related with pressure, can be related to concentrations. That's not the problem. But they all have the same form. Whatever is the variable that we know, we control, and whatever is the function we're looking for. So here we have a function that we call f of t, and that's the function. If I take this function that the only condition is has to be defined, has to be a function that's defined for all values, possible values that I'll be considering of my independent variable. In this case, I call t. But as I told you, you can call anything. And we are considering that this function is well defined. It's a defined function. It has a value of function for any value of t from 0 to infinite. This is called defined function. Okay, we have this function. And then we can define what we call the Laplace transform of this function, which is nothing more than taking the function, multiply by an exponential of minus st, right? So I multiply the function by exponential of minus st. Who is s? Well, of course, s is a variable, a new variable that I define, and has, you know, you will know that exponential of something, this thing cannot have unit. So s, if we are dealing with unity, if it is time, probably s is the inverse of time. It's always the inverse. So when we do the Laplace transform, we're going from one variable t to another variable s, and normally if they have dimensions, they are inverse each other. It's like going to space, real space, to reciprocal space, that we call, right? It's the inverse of the space. This we do all the time in analysis of circuits, because we want to know if we use time, we want to go to frequency, which is the inverse of time. If we use space, we go to the inverse of space, that's called k vector or whatever, reciprocal space. So doing the Laplace transform, we are modifying, we're going to the function to the reciprocal space of the variable that we are considering. Time inverse of time, space inverse of space, and so on. So normally we are taking a function to a different space, which is the reciprocal space of the variable that I'm considering. There are so many important things that has to go to the reciprocal space to be able to work, right? We know, engineers know that we needed to work sometimes in frequency domain or in time domain, right? Those are time domain. If you want to know how something varies with time, is one thing. If you want to know how the same phenomena evolves with frequency, is the reciprocal of time. So Laplace transform of a function is going to the reciprocal space of your coordinate. So, I mean, that's easy, right? So this is the Laplace transform of the function. And normally we say that if we can do that integral, the function f of s, and remember, s is the reciprocal of t, is L Laplace of f. Sometimes we call L, this L, right, this special L of s, of f, represents the Laplace transform of a function in t space, depending on t variable, and now we produce a function that's depend to s. And they have to be connected, you know. T and s are variables that work in reciprocal each other. And then I already anticipate to you saying in what situations the reciprocal of time is important. It's when you want to know frequency, right? And I already told you when it's reciprocal of space, when you want to go to k vector, for instance, dealing with functions that are periodic in space or time and so on. So it's easy. When we're doing the Fourier, the Laplace transform, you know, Fourier is another transformation that's very important in physics or in engineering. So here, doing the Laplace transform, we goes from t to his reciprocal variable. And of course, you know, depending how is the behavior of this function, the Laplace will have a specific behavior. Suppose that this function here, you know, it goes with some exponential behavior and multiply by another exponential. One may compensate the other or vice versa and so on. Right? I could spend half of the lecture explaining Laplace transform and interpretation for the Laplace transform, but we gotta go to use it to solve the equation, so I can't stay explain too much about Laplace transform. But you know, Laplace transform of a function is something very, very important for engineering. Right? It is an integral transform, we say, because it's not only transform the variable. All the domain of time here, or t, will be expressed in S. That's why you see how important is the Laplace transform. How the function depends in the whole domain of the variable t will be represented in the dependence of the variable S. If you see a function that's periodic in time, if we speak about time, look into the whole variation of this function along time will be in the Laplace transform of this equation and will be expressed in each S. So the function here, that's important to know. When we do the Laplace transform, we are mapping the whole domain of the function in a new function. It's not that one point of t will come to one point of S. No. All the t will come to one point of S. That's very interesting. That's why it's called integral transformation, because depends on the whole. Depends on all the domain of the function for defining. And that's why it's not only a variable transformation. It's a whole function transformation. And that's why it's important, because we're always looking for reciprocal domains of the functions, and this is a good transformation for that. And we're going to represent that way when we're doing the Laplace transform, which now you know what it is. Multiply the function by the exponential of minus s times the variable of the function, and integrate in the whole domain, where the function is defined and then you are considering here. Okay. Well, this is just well, there is a very nice philosophy, you know, behind defining that way, as you're gonna see as we develop our lecture. Very good. So this is the definition of Laplace transform. So if we know to do the Laplace transform, we know to do the inverse of the Laplace transform, right? And that we call the inverse. We call it this minus 1. This is the inverse of the transformation. And the inverse of the transformation we define by, if we know the function and we know this relation, we basically identify what function give you this Laplace transform. And this is called the inverse operation, right? There are ways of doing this. There are ways to identify. It's easy. Normally we have tables of transformation, right? Either you know, save it in different ways, and we can somehow do well here. Okay. So let's do it. So normally we're gonna have to know to do the inverse. And the best way is knowing a collection of functions, and when we have a function and we know its Laplace transform, we just come and define the inverse. So this is the inverse transformation. We're going back to the original variable, okay? Let me give you some examples. So the first example I'm going to give you is a function that's a constant. If the function is a constant, I call 1 because any value I put here will come out of the transformation. So if I make for 1 is the the number that appears here will be whatever is the number here. If it is 10, will appear 10. If it is anything, any constant. So this is the Laplace transform of a constant. We define it, if the function is this constant, we define the Fourier transform as the integral of the constant, which is 1, and I already kept here explicitly, integral of exponential minus st dt from 0 to infinite. Everybody knows that the integral of an exponential is exponential from 0 to infinite, and in the infinite, if s is positive, define is 0. So I end is minus because there is a minus here, right? And then this end by being 1 over s. So the transform of a constant is 1 over s, or is the constant divided by s, because if I have put 10 here, this will be 10, everything will be 10, right? So the Laplace transform of a function is just the inverse of s. So the function f of s is 1 over s if f of t is 1. So that's the Laplace transform of the constant function. Another interesting example is Laplace transform of exponential function. If we have an exponential function, then the Laplace transform will be, f of s will be basically integral from 0 to infinite of e to the minus st times e to the at dt. So this is actually e, this integral is, this term here is basically a single exponential that is minus s minus a of t, right? And we all know what's integral of minus s minus a times t is the same from 0 to infinite. And then, of course, we just redefine the exponential, and the Laplace transform of an exponential is basically 1 over s minus a. Observe that the Laplace transform now, when you get to the point where you are considering this variable s, because this is a function of s, a continues to be a constant. So the Laplace transform of this is 1 over s minus a. And if this cancel, of course we have a divergence on the Laplace transform, because we basically integrate from 0 to infinite of a constant. And we all know that this gives infinite. That's why there is a divergence when the constant and the new variable of the Laplace transform are equal. So I just give you 2 examples. But there are many, many examples we needed to consider for this, right? And we can build up a collection of Laplace transform of many functions. And of course, because the Laplace transform is defined as an integral, the Laplace transform of a sum obeys basically the property of the integral. And we know that the integral of a sum of functions is the sum of integrals. So, because of the properties of the integrals that we learn very well on the basics calculus, that extended to the Laplace transform. So one property is very important is this. The Laplace transform of a sum of functions is just the sum of the Laplace transform. So if we have a sum of functions, the Laplace transform of the sum is the sum of the individual Laplace transform of each of the function. And of course, when you multiply the integrand of the integral by a constant, this constant comes out from the integral. So the constants that appear here are also multiplied the Laplace transform. So the Laplace transform of a sum is the sum of the Laplace transforms. Right? And this is important. It's very important to know that and many other properties that we're going to do it is important to know. Right? Okay. And now that we define the Laplace transform, we can come and consider many functions that we believe are important. You know, we know the most important functions we're going to deal with, especially depending if we are dealing with electrical, if we are dealing, there are many functions that appear all the time. Exponential, trigonometric, power law, that kind of thing appears all the time. So we can consider many elementary functions and do the Fourier, the Laplace transform. Oh boy, I'm with Fourier. Maybe next is using Fourier to solve the equations, right? Okay, so consider the following functions. Constant function. If I have a constant function, I already verify what is the Laplace transform. Now I want a linear function, t. F of t is t. So we go and do the integral of t exponential of minus s of t dt. And we know that this you transform, you make a transformation of variable, and you can easily show that the Laplace transform is 1 over s squared. In fact, if I am a quadratic function, t squared, and I do the Laplace transform, I get 2 divided by s cubic, right? And then I can generalize, and this is important because the power, if I have in my differential a function that's a series of powers of t, the Laplace transform will be the series of transformation of each term, and each term that depends on t, like to the nth power, and n being an integer bigger than 0, this is an important restriction here, we get a Laplace transform that's n factorial divided by s n plus 1. Right? Yeah, we all know when we integrate, we always get to an extra term in the exponent. That's why this here is always one unit higher from the exponent of the power that we have. Okay? And in general, when this is not an integer, we have to define t of a with a generic a is normally defined in terms of the gamma function divided by s to a plus 1. So when a is any variable here, we needed to identify that way, right? But we're going to deal a lot with this type of Fourier transform, which means Laplace transform, I'm sorry. We're going to deal a lot with the Laplace transform of power law type of terms. Very good. Now, that's all the functions we need. There are many, many functions we would like to have. Suppose it is an exponential. So we already showed that the Laplace transform is 1 over s minus 1. And if I have a cosine function, well, the Laplace is s divided by s squared plus w squared. Or omega squared, right? Because this is cosines of omega t. the Laplace transform is s squared plus omega squared. If it is a sine function, I know that sine sometimes is si, but I like to always to put se, you know, to obey the language here and everything, the origin of the notation. So sine of omega t has as Laplace transform omega divided by s squared plus omega squared. If I have a cosine, hyperbolic cosine of at, then the Laplace transform is s divided by s squared minus I squared. Of course, we all know that cosines, whatever the s is equal to a, we start to get divergences. So it's very nice to understand what those divergences in s means when we have. That will be like resonances when we do the Laplace transform. If I have a hyperbolic sine now, the Laplace transform is a divided by s squared plus minus a squared. So the sine hyperbolic of at has as Laplace transform of the function a divided by s squared minus a squared. And so on. You see, we could do many different Laplace and make a table like this. This is a nice table. You know, it has a lot of functions that will appear in many solutions of differential equations, right? Okay, so this is Laplace transform, and we're gonna use the Laplace transform, and we gotta know that kind of behavior of the functions and the Laplace transform of the respective function. But that's not all for us to use Laplace transform to solve differential equation. We have to collect a few more properties. There is one very important property, because the structure of Laplace transform is such that when I multiply a function by exponential, basically the Laplace transform is only the displacement of the new variable. So the Laplace transform of exponential of at of f of t is actually, if I know if f is the Laplace transform of small f, then the Laplace transform of exponential of at times f of t is basically the Laplace transform now on the variable s minus a. I already showed to you this, because when we do the transform of exponential multiply the function, that just get minus s minus a on the top, and then you redefine the variable, right? So that's an interesting property, because we know that the Laplace transform of t to the n power with any integer is equal to n factorial divided by s to the n plus 1 power, right? That's why we define here. When we build up this table, we wrote this expression here. T to the n has as Laplace transform n factorial divided by s plus 1 on the power. So when I take this, so I know already what is the Laplace transform of this function. Is n factorial divided by s to n plus 1 power. So if I multiply this function by e to the at, I just substitute s by s minus a. That's what this property is giving. So this is a nice property, because exponential appears everywhere, right? So we know how to identify. So that's a nice property. Multiply a function but by an exponential, just to displace the variable on the Laplace transform. Another example. We have the cosine of omega t. We already showed that cosine of omega t has as a Laplace transform s divided by s squared plus omega squared. So now if we multiply cosines by exponential, we just displace s. So by knowing the Laplace transform of cosines of omega t, we know immediately what is the Laplace transform when we multiply by exponential. That's a nice property, and we're gonna use a lot, right? But what we want really is to make transformation of the differential equations. And differential equations, we all know, is a collection of derivatives. So we need a collection of derivatives. So we have to know what is the Laplace transform of a derivative of a function. If we know, no, here by definition we know we have a function. Suppose we know the Laplace transform of this function. Can we know what is the Laplace transform of the derivative? And the answer is yes, we can. And we can do the algebra. We don't have time here to do all this. But if I know the Laplace transform of the function, the Laplace transform of the derivative of the function is related to the Laplace transform of the function minus the value of the function in a specific, in the inferior limit of the integral, which is 0, because we start from 0 and go to infinite. So if we know this guy, if we know what is the Laplace transform of the function, we can get the Laplace transform of the first derivative of this function. That's a very powerful property, because that's allow me, I'm not deducing, but it's not hard to do it. It's just take the definition of the Laplace transform, take the derivative. You can go on with this and make the proof. This is easy to prove. If I have the function, it's easy. The Laplace transform of the derivative is like putting the s in front of the function, of the Laplace transform of the function itself, and subtract the limit. You know, if you know, here is very important to know that when I know a derivative of a function, I'm only going to know the function if I give you a value, an initial value, or a boundary condition. And here you have to know the value of the function in 0 to be able to get what is the Fourier, the Laplace transform of the derivative of the function. So this is a nice relation between the Laplace transform of the function with the Laplace transform of its derivative. And that's now start to depending on the initial value of the function. So, but this is not surprise, because you remember, to solve a differential equation, you need to know how to solve, but you need to have some initial values to be able to specify the full solution. And the Laplace needs that too. Now, let's take the second order derivative of a function. If I know the Laplace transform of the function, can I know the Laplace transform of the second derivative? Yes. Just the Laplace transform of a derivative of a function is nothing more than s squared times the Laplace transform of the function minus s times the value of the function on the initial condition minus the derivative of the function in the initial condition. So now we needed to know two values to be able to specify the Laplace transform of the second derivative. So we need two initial conditions. We gotta know the initial values of the function and its derivative, the first order derivative, to be able to determine the derivative of the second order Laplace, to be able to determine the Laplace transform of the second order derivative of the function. Another very important property, because I'm starting to relate it, derivatives with function. Here derivatives disappear. I only needed the initial values of the derivative of the function. which normally, as I said before, solving differential equation, if you're going to solve the second order differential equation, you gotta have two initial conditions. One for the value of the function, one for the value of its derivative. It's like knowing the position of the object and the velocity to be able to determine the acceleration in any time, or to be able to determine it, to build up in the Fourier, in the Laplace space here now. But this is normally when you're solving those equations that represent physical phenomena, you have to establish, you know, even though you have a law, I know what is the acceleration. To be able to build up velocity, I have to know the initial values of velocity. If I want to know the position, I need to know the initial value of the position as well. This is more or less what I want to say. So we have a very specific way of doing. If we know the Laplace transform of a function, we can get the Laplace transform of the second derivative of this function. So you start to see that I'm transforming derivative in functions, right? By doing the Laplace transform of derivatives, I'm going to end with functions. This is f of s, and this is f of s, too. So derivatives will be now transformed into functions. Of course, we can generalize it. You know, I stop in the second order, but you may have a third order, fourth order, and there is a logic on this. You just start. If it is 3, if the order of the derivative is 3, this is s to cubic times the Laplace transform of the function, and then minus s squared times the value of the function, minus s times the first derivative in the initial value, minus the second derivative in the initial value, and so on. So this is for the third order. And of course, just to be completed in this tutorial, I just generalized and say, well, if you wanted the Laplace transform of any order, any derivative of the function, of any order n, is related to the Laplace transform of the function times, you know, s to the n, as we saw, always, but then you need to know any minus 1. If I'm dealing with the Laplace transform of the nth derivative, I need to have, you know, the values, I need to have any initial values to be able to construct the Laplace transform. Very simple. This is algebra, right? And what is important is I'm transforming any order derivative into the Laplace transform of the function itself. And the rest of it are initial values. This is very powerful because with that, we will be able to solve differential equations by doing the Laplace transform of the equation as a whole. Take the Laplace of the whole equation, and then that's going to be transformed in an algebraic equation. Very good. Examples. If I have a function cosine and the initial value is 1, I know that the first derivative is this and the original value is this. The second derivative is this. I could put value, and then just for an example, I can take the second derivative. We know that the Laplace transform of the second derivative will be minus omega squared times, because the 0 and then there is the 1 that cancels. So what we have here is basically, when I do the second the Laplace transform of the second derivative of cosines, I get omega squared times the Laplace transform of cosine. So I build up this very easy. You see, it's much easier. I don't even know. If I know the Laplace transform of the function, I can immediately write, by following those rules, what is the Laplace transform of any derivative. That's very important. That's very powerful. Okay. You already start to build up in your mind how we're going to use Laplace to transform equations, differential equations, in equations easy to be solved. And that's what we're going to see in the next lecture, a few examples.